Hello, and welcome to my report on the Week 10 readings. This week, we were introduced to Faraday's law and the interactions of a falling magnet. We looked at a falling magnet's interaction on a conductive loop, what Faraday's law can tell us about induced currents, and then lastly, the forces acting on the magnetic dipole falling towards a conductive loop. Faraday's law is a new topic for me, however, one of the concepts central to the topic was flux, which we looked at last week. Also, this content builds on our knowledge of electric and magnetic fields. To begin with, as an introduction to Faraday's law, we considered a falling bar magnet and a static surface underneath it. Given the size of the area below, we could treat the magnetic field as being constant across the entire area. This assumption allows us to calculate flux on the area as the product of the magnetic field and the area. Due to the setup of the falling magnet also, this means the flux changes with respect to time because the magnetic field strength increases as the magnet gets closer to the area. The equation for the change in flux with respect to time is the flux at T sub f minus the flux at T sub I, all divided by the difference in time between T sub f and T sub I. As the falling magnet is a source of an electric field, here we can use a new version of the right-hand rule to identify the direction of the electric field. Here you place your thumb in the direction of the negative change in flux with respect to time, and your fingers will curl in the direction of the E field. We then looked at Faraday's law with respect to induced currents. Here we saw that the magnitude of the flux time derivative is an electromotive force. Still considering the same falling magnet, this time we include a wire loop around the perimeter of the small static area. A current I around this loop is induced by the falling magnet. The energy in the loop comes from the gravitational potential of the magnet. We also looked at Lenz's law, which tells us that the loop produces a magnetic field which opposes the change in flux. This was expanded on in the last reading, where we looked at the force on a magnetic dipole. Here, we looked at the force on the falling magnet due to the wire loop. We were looking for F loop on magnet, but due to Newton's second law, we can find F magnet on loop and reverse the direction to find the force we are looking for. This force is equal to the current times the cross product of delta L and the magnetic force due to the magnet, which in turn is equal to the product of I, 2 pi, the radius of the static area, the magnetic field, and sine theta. We will explore this concept further in an upcoming lab. The hardest topic for me this week was understanding how the moving magnet equates to an electromotive force. After reading the physics book page, however, I feel I have a better understanding. Thinking about this topic with respect to my major, computer science, I find these methods of generating current particularly interesting. I'll be interested to learn more about how generators work and how these magnets are used in that context. Thank you very much for listening.